what I want to ask you is, initially we have got a huge cloud of gas. Okay, a big one over here. It's a very huge cloud of gas, and at that time, out of the four fundamental forces, right? Strong, weak, electromagnetic, and gravitation. Now I am talking about a huge cloud of gas, neutral particles, neutral atoms. So electromagnetic out. What about strong interaction? Come on, we are talking about a huge cloud. I am talking about a scenario where if one atom is sitting right next to me, the other atom is outside the solar system somewhere. So what about strong interaction? No case. What about weak interaction? Nothing. So only one there, gravitation. Now it will be very small, but it will be there. And take into account that there are so many atoms, more than 10 to the power 20, 30, 40 atoms or so. We will do the estimate over there as well, and I will talk about this later on. So only gravitational force is significant in this scenario. Right. Now, what will gravitation do? It will keep on collapsing. This huge bond on the blackboard, and after a lot of time we will have a situation like this. What will happen? Suppose in this case, if one atom is sitting right next to me, the other atom is in New Delhi. Now this is a very dramatically different scenario. Okay. Previously it was outside solar system, now it is in New Delhi or something like that. And then it will be near Howrah Bridge and so on and so forth. Two atoms will come closer to each other because it is collapsing. And what will happen? There will be chance that they will come and collide with each other and so on and so forth. So gas pressure will be there. Slowly. It's not that it was not there, it was very small. So I am not taking it into account. But here it will start keep on increasing, and eventually it will be this gas pressure which will oppose the gravitation. And as a result we will have what? Hydrostatic equilibrium at some stage when the two of them will be equal and opposite to each other, and we will have a fixed radius and so on and so forth. Now suppose what happens after that? I am not talking about fusion or whatever right now. I am just more interested in this scenario of what will happen if I keep on collapsing. What will happen? So the next stage is the scenario where one atom is sitting right next to my one hand and here is another. What will happen? Again nothing will happen. Why? The distance of 1 centimeter. Atomic dimension is angstrom. But if I keep on compressing, right, if the gravitation keeps on collapsing the stars, what will happen? Eventually a time will come when the atoms will come very close to each other, near atomic dimension. And what will happen? Their wave function will start to overlap. Okay, good. What's the problem? Till now we are talking about classical scenario. No wave function. Now this is the first time I am talking about wave function because ultimately they are quantum particles, right? Now when the wave functions try to overlap, what will happen? It will be possible for two electrons to occupy the same state, the same quantum number. But tell me, will it happen? Of course no. Pauli's exclusion principle tells us that for fermions it will not be the scenario. And electrons are fermions. Right? Same for neutrons and protons also. They are also fermions. So what will happen? Two electrons will not have the same state with the same quantum numbers, and this will result in the not complete overlap of the wave functions. Right? So as a result of this fermionic nature of the electron, right, what will happen? A pressure will be generated. Now this will be a new pressure. Additionally, now at this time what will happen? This gas pressure will be much smaller compared to the gravitational pressure. And the new pressure, which is known as degeneracy pressure. This is due to the fact that the electrons will not be in the same state, the same level with all equal quantum numbers. And this fact, in fact, this inhibition of electron, this causes a degeneracy pressure. Okay. At this time, the structure will change of the star. Now I am talking about the degenerate scenario. Now, first we are talking about electrons. Why not protons and neutrons? Because their mass is 2000 times smaller. So in this case, a scenario will come where we will have white dwarf and so on and so forth. Eventually, suppose the initial mass was very large, and as a result, even the degenerate electron pressure, let me write it down, E. Okay, so here only gravitation, now gas pressure dominant, now electron degeneracy pressure is the dominant one, which is resisting the gravitational force. Next scenario, suppose the mass was very large. As a result, even this electron degeneracy pressure is unable to inhibit the gravitational force. What will happen? It will keep on compressing to a point where the nuclear degeneracy pressure will kick in. That is degeneracy pressure due to neutrons and protons. Okay. So here we have hydrostatic equilibrium. That is the first one which opposes the gravitational force, gas pressure, constant radius. The next case is over here, white dwarf, where electron degeneracy pressure will completely inhibit or equate against the gravitational force. Next stage will be neutron. Here the degeneracy pressure due to neutrons will be equated against the gravitational pressure, and we will have a neutron star of a constant radius. So these things are important. Look, it is in fact this opposing nature of the force which is able to describe so many different types of stars. This is a normal star, this is a white dwarf star, this is a neutron star. The fundamental difference is the opposing force. Here gas pressure, here electron degeneracy pressure, here only degeneracy pressure due to neutrons. What about the protons? This I will discuss when I talk about neutron star. Okay, any question?